Hey P-Physicsy, this is Horner. We're looking at a car on a hill. It's coming around a curve though, so this car is coming kind of at you. The curve would continue around. And so we want to find out what is the speed for which this car can be on the curve if there's no friction. So this is really an icy hill. So you can't go very fast, but we can do it. If you go too fast, you're going to move up the hill. If you go too slow, you're going to slide down the hill. Now this one's a little different because the force that we're creating by the hill, by turning on that hill, is actually due to the centripetal acceleration. So there's something going in this direction. That changes how we're going to draw our free body diagram for this one. So to draw this one, notice that I have my red dot is my car, straight down is going to be mg, and then going up this way is the normal force, but we're going to make our axes straight up and down and left and right. So this is positive y, this is positive x. It's going to make it a little different. And also it's different because let's go ahead and draw our components. Our components are going to be like this. So instead of having it parallel to the surface, and we only do that, we do that normally because there are forces going up and down the hill. We're not worried about those this time. There aren't any. They're only going left and right, up and down. So that's a brand new thing that you'll see only in C. This angle right here should be that 15 degrees. It's the same as the angle that is right here. And then this is Fn sine of the angle, and we know that this side is Fn cosine of the angle. So let's look at the y directions first. So some of the forces in the y should be equal to 0. Car's not going to move straight up and down. So we have Fn times the sine. Oops, sorry. This is going to be Fn, we're doing the y direction, not sine, but Fn times the cosine of the angle minus mg is equal to 0. And so we can say Fn cosine of the angle is equal to mg. Let's solve it for Fn, that'll help us out later. That's equal to mg over the cosine of the angle. Do the same thing in the x direction. So some of the forces in the x direction, we do have an acceleration. It's that centripetal acceleration. Let's go ahead and put in the only thing that's going in the left to right direction is Fn sine of the angle, and it is equal to MAC. Now we could say, well, but that's to the left. Technically that would be negative. You could do that, but they'd both be negative, and then the negatives would cross off and they'd both be positive. They want us to find the speed. Here we have acceleration, so we don't want acceleration, but we do know that acceleration is equal to v squared over r for something turning in a circle. So let's rewrite this. Fn times the sine of the angle is equal to mv squared all over r. We have an expression for Fn, so we can get Fn out of there. So let's take this and move this here. So now we have mg times the sine of the angle all over the cosine of the angle is equal to mv squared over r. Mass will not matter here. The g needs to say sine over cosine is tangent, so this would be g times the tangent of the angle is equal to v squared over r. We're going to multiply both sides by r and take the square root of both sides so that your final equation should be v is equal to the square root of g times r times the tangent of the angle. So just to review again, do make sure that you make your axes straight up and down, left and right, because the acceleration is directly to the left, which is really weird compared to what we normally think of. Now we need to solve, so we're going to do the square root of gravity here is typically we can use 10. The radius of curvature is 100, and then we're going to do the tangent of the angle. And got to make sure you're in degrees, so that'll be the tangent of 15. And you should get an answer close to about 16 meters per second. If they use 9.8 and got 16, then 10 is going to be a little bit different, but that's the first part of the problem. Let's go ahead and take a look at the second part of the problem. It says, on a dry day when friction is present, the automobile successfully can negotiate this at 25 meters per second. And so what we'll do is we will go ahead and they want us to draw all the forces on the automobile now. So let's go ahead and do this. So here we go. We've got up is going to be the normal force. We know that straight down is mg, and then going this way is going to be our force of friction. So there's all of our forces. You'd end up with 4 points for this actually, because they gave 1 point for each, and as long as you didn't draw anything wrong, they gave you an additional point. So nothing like bonus points on the AP Physics exam. We're going to leave that diagram right there, and it says determine the minimum value for the coefficient of friction necessary to keep this car from sliding as it goes around the curve. So here we go again. Let's think about x and y again. We are going to make x and y again in these directions. So this would be positive y and positive x. And the only thing we have to remember here is we still have an acceleration pointing in that direction. So I know that the acceleration is straight to the left. So we're going to need components again. We're going to have components here, and then we're also going to have components on our F. So that makes it a little different than what you've seen before. This angle right here we know is theta, and this angle right here is also theta. So this is going to be F times cosine of the angle. We know this little side of the triangle, so I'm going to make it blue, is F times the sine of the angle. This one up top is going to be Fn times the sine of the angle, and this is Fn times the cosine of the angle. All right, let's think about everything in the y direction. Sum of the forces in the y direction. Here these should be equal to 0 again. So let's look at all the ones that are in the y direction. Going up, we have Fn cosine of the angle. And then going down, we have F sine of the angle. And we also have mg going down, so that's equal to 0. All right, so now we need to do this in the x direction. So sum of the forces in the x direction should be equal to mv squared over r. And so let's do all those forces. The first one we've got here is the normal force times the sine, of the angle. So normal force times the sine of the angle plus F times the cosine of the angle, and that should be equal to mv squared over r. In order to really solve for mu, and the reason we have mv squared over r here is because remember this is really ma, and a is equal to v squared over r, so ac is equal to v squared over r. In order to solve this correctly, we know that the force of friction is equal to mu times n, and they want us to find mu. So we really need to know what F and n are. So we've got to use some pretty tricky trig to try to combine these two. But I have a solution that might be a little bit easier to do. And so I'm going to kind of show you that solution here. Let's go ahead and draw our free body diagram again. I'm going to do it in this color. And we've got mg going down. We have the normal force going up in this direction, so we'll put Fn. And then we do have friction going down in this direction. So this is friction. So in a different color, because what I'm going to do is I'm going to change your axes. I'm going to change your axes to be in these directions. So this is plus x, and then this is going to be plus y. And what we're going to do is let's think about that mv squared over r, that centripetal force. That centripetal force we know goes left-right. And so to think about it, if it's going in this direction, we can actually make it so that it's got some components. So let's make it into components that are in the same direction that we have here. So if this is mv squared over r, we can make this side right here mv squared over r times the sine of the angle. We can make this one mv squared over r times the cosine of the angle. But be careful, because this thing right here is really due to that acceleration. The other thing I want to do is break up mg into components. Oops, let's change color. Break up mg into components that we're used to using here. So there's our angle. This would be mg times the cosine of the angle, and this is mg times the sine of the angle. Now everything is in our directions. And that's what we want, because we want it in the Fn and the F direction. All right, so hang with me here. Let's try to go ahead and set up some of the forces for our new diagram in the y direction. In the y direction, notice we are not worried about not worried about anything other than we do have an mv squared over r, so it is accelerating in this direction. It really is. So we're going to need to put mv squared over r, but we're going to have to do that times the sine of the angle. So yeah, we need to do that in terms of sine of the angle. So we'll put that sine of the angle in. Now let's go ahead and think about everything that is in that direction. So we're going to do Fn minus mg cosine of the angle, and that's equal to mv squared over r times the sine of the angle. But we want to solve this for Fn. So we're going to say Fn is equal to mv squared over r times the sine of the angle plus mg times the cosine of the angle. Let's do the same thing in the x direction. So sum of the forces in the x direction is also going to have mv squared over r in it, because now we've defined x as this way and there is something going in that direction. It's mv squared times the cosine of the angle. And so now we've got the force of friction. So here we've got F. And then also in that direction is mg sine of the angle. So F plus mg sine of the angle is equal to mv squared over r times the cosine of the angle. I'm going to move in this direction now. So at this point we've got a mess. I realize that. I'm going to erase some things here so that we can go ahead and finish up this problem. And we're moving over this direction. We're going to bring this thing and resolve it up here. So this is F is equal to mv squared over r times the cosine of the angle. And then we need to subtract mg sine of the angle. All right. So now we have an equation for Fn, and I'm going to circle it in yellow. And we have an equation for F, and those are the two things we needed in order to find U. So let's just say U then, or mu, is equal to F, which is mv squared over r times the cosine of the angle minus mg sine of the angle, and that will be over Fn. And notice that Fn is also mv squared over r sine of the angle plus mg cosine of the angle. So let's get rid of, we've got a lot of m's and r's here, so we're going to get rid of the m's, boink and boink. We're going to get rid of this m and this m. We're also going to go ahead and leave the r's where they are, so we can say this is going to be v squared times the cosine of the angle minus g times the sine of the angle. We're going to do that over, now we've got this guy here, so this is v squared times the sine of the angle plus g cosine of the angle. And I know you're looking for the r's. What we'll do is we've got this one is over r, this one is, sorry, this one's over r, this one's over r, so we can multiply the top and the bottom by r, and so that'll get rid of this r and get rid of this r, so we'll have gr sine of the angle and GR cosine of the angle. If you're really confused on that, come see me and I will help you. Now that we have everything, we can put all of our numbers in. I won't go any further than that other than to tell you our mu value here is equal to 0.32. And you have to put all your values in. I'm just not going to do all that math for you. You should be able to do that. And that's the end of this terribly long problem.